Let's talk about digital recording. Okay, let's go through a few terms before we get into the nuts and bolts of how it works. Sample rate is the frequency at which the analog signal is sampled. ADC is analog to digital converter. DAC, digital to analog converter. Bit depth is the number of bits or binary digits used to store the voltage, and it's called quantization. Let me actually sort of draw on the board a little bit about how this works. Time, amplitude. We've got a signal that looks like that, an analog signal, analog voltage. The sample rate is in the time domain and splits that up into samples. And at each sample, it takes a sampling of where the signal is. That's on the horizontal axis is the sample rate. On the vertical axis is the bit depth. These represent digital numbers. Where the sample is, closest bit is where it's assigned. Let me give you the overall flow. So that gives you a little bit. Sample rate is on the horizontal axis, the time axis. So it's a rate. And bit depth is dividing the amplitude of a signal into different segments. Okay, so here's the block diagram of how digital audio works. The audio comes in, it goes through an anti-aliasing filter, and I'll discuss what aliasing means in a second. And then it goes into a sample and hold system where it takes a sampling of where the signal is and holds that voltage. And then it gets assigned to a digital number in the analog to digital converter. Then, of course, it's digital numbers in a sequence and can be stored on your hard drive or any digital sort of storage mechanism. And then when it's played back, it goes to a digital to analog converter, changes those digital numbers back to analog voltages, and then a recovery filter changes those voltages back to a continuous signal. Then you get audio out. Anti-aliasing filter, basically a low-pass filter with a very, very extreme stop band. Stop band is where it doesn't allow any frequencies above that to get passed, and filters them out very quickly. And the bandpass is where the usable audio is. So you'll see that the sample rate and the bandpass filter are kind of linked together through a theorem called the Nyquist theorem. And I put it here, even though I'll go a little more in depth in a minute. Anti-aliasing filter is a low-pass filter. Frequency cutoff of the filter is the sample rate divided by 2. That's called the Nyquist frequency. So this is how sampling works. So you've got, on the horizontal axis, you've got your samples, your frequency of sampling. On the vertical axis, you've got your bit depth. And so it takes and basically takes a sample at a specific time and holds that voltage until another sample comes along and changes that voltage. And it ends up looking like this in the sample and hold picture. Okay, so it takes a sampling and holds it until the next sample comes along. So if we're looking at a sample here, then the next sample time comes along and it gets this voltage, holds it, and the next sample comes along, it gets this voltage, and so on. And it just continues. So you get this kind of odd-shaped but sort of a stair-step kind of looking picture for an analog signal. What it ends up doing is it then takes your analog to digital conversion and it takes this pulse of the sampling, holds that voltage, and then takes that voltage and assigns it to different numbers. Different numbers in the digital domain are the different bit depths. Now, if you ever worked in Pro Tools, when you start setting up a session or in Logic or in any DAW, I think they'll ask you for what sample rate you want to use and what bit depth you want to use. What they're talking about is how fast you want it to sample the analog signal and how many divisions on the vertical axis would you like to have accessed. Naturally, just as a rule of thumb, the slower the sample rate means the less quality of the digital conversion from analog to digital. The same thing with the bit depth. The smaller bit depth means that there's going to be less divisions, so naturally it's going to be less accurate to the analog signal. So it's almost like in visual arts, the DPI is the how many definitional points per square inch. High definition has more definition points per square inch. Low definition has less. Same thing with digital recording. The higher the sample rate and the higher the bit depth, the more accurate it translates the analog signal into numbers, so it can retranslate it back to analog most accurately. Now, the interesting thing is if you take it to the limit, now let's say we could go ahead and have an infinite amount of samples, not just 44.1 thousand times per second, or 48,000, or 96,000, or 192,000. Let's say you could have 1,000,000 samples per second. All of a sudden, the divisions on the horizontal axis get smaller and smaller and smaller, to the point that if you have an infinite amount of samples, it becomes analog again. So it's basically thinking about an analog signal, breaking it up into small enough chunks that the limit is, if you have an infinite amount of small chunks put back together, it becomes analog again. Anyway, so that's the process. The sample rate gets converted into samples of where the signal is. And then you can see in this picture, the more samples there are, the more accurate this little staircase staircase picture sort of replicates what the analog signal is. And the fewer samples, the much more inaccurate it is. Okay? So then the numbers that are created by taking these samples and assigning a bit to each of these samples turn into a string of numbers, string of digital numbers, of ones and zeros, and then the computer memory can manipulate them. The digital numbers are sent to the RAM and then manipulated with the DAW, and digital numbers are sent to the record hard drive for storage. And there's thousands and thousands and thousands of ones and zeros being sent to your hard drive at all times. The computer itself has to remember where on the hard drive all this stuff is stored. So the way that hard drives work, it's pretty impressive, is that they're split into divisions or sectors, and it uses each sector, it's magnetic as well, it uses each sector to remember different digital words. And if one sector gets filled up, it'll find a free sector and go to that and continue to write the data. So when you're reconstructing this, it has to know where it put all of these ones and zeros and in what sequence. Because if you change the sequence of the ones and zeros, you actually change what the analog recording was in the first place, or what the analog signal was in the first place. So it's pretty impressive how the computer itself can keep track of where each sample is going on the hard drive, bring it back, and reconstruct all this. That, to me, is a real engineering marvel. Okay, so digital to analog, the assignment of numbers to the bit depth, the voltage is held and converted at the next sample time. So it's called a sample and hold function. So it holds that voltage until the next sample comes along. And this gives you a little bit of idea of how it works. So your digital input code and your analog voltage out. So it sort of gives you an idea that it relates really very accurately to whatever voltage is coming in and going out. So we talked briefly about what the Nyquist frequency is and why you have to have, on the input stage of this whole recording device, why you have to have a filter. Let me explain that more fully. Okay, the highest frequency that can be reproduced accurately when the signal is digitally encoded at a given sample rate is the Nyquist frequency. And theoretically, the Nyquist frequency is half the sample rate. So let me explain a little more clearly. Let's take a random signal, some frequency, and I've expanded this tremendously in the time domain on the horizontal axis. So let's say this is a very high frequency. And our sample rate is here and here and here, because it's sampling that slowly compared to this high frequency. So you go here and you grab a sample, and you go here and you grab a sample, and then the computer has to make heads or tails of this. So it takes this sample over here, it takes a sample over here. So the computer itself is thinking, well, this frequency could be this, it could be this. So basically what it creates is, if you have a sample rate that's slower than the highest frequency trying to be recorded and coming into the system, it creates what's called alias frequencies, like alien frequencies, which is true. So you get all of these extra frequencies that really don't exist in the original sound. For signals with frequencies between half the sample rate and the sample rate, the resulting waveform can be calculated by the formula I listed here. And here's actually a better picture of what I'm talking about. So if you've got a high frequency signal that's being sampled like this, the blue waveform could also be represented by the same sample points. So now you've got two frequencies that can be represented by the same samples. That's not a good thing to have. Let's just say we take the highest frequency that can be recorded, right, as a sine wave, and we put a sample at the maximum. So if we've got a sine wave, and we put a sample at the maximum and at the minimum, that means we've got two samples per wavelength. Then the computer will know, okay, it's got to be this frequency. So that's why we take and put the signal through a really severe filter to filter out all of the super high frequencies, even frequencies we can't hear, because as we discussed before, in the spectrum, there's an infinite amount of frequencies that are created no matter how quiet, but they're still there. So to protect the system from creating some alien frequencies or aliasing, it goes ahead and filters out all the high frequencies that are more than half the sample rate. So let's say you sample at let's say you sample an easy one. Let's say you sample at 50,000 hertz, 50,000 samples per second. What's the highest frequency that you can capture at that frequency of sampling? 50,000 sample rate means you can capture 25,000 hertz accurately. Okay, so the Nyquist frequency is half the sample rate. The Nyquist frequency is the highest frequency that can be recorded accurately.